Hi everybody, today we're looking at confidence intervals. So what a confidence interval is basically it's an interval in which the population mean, or we're pretty sure the population mean lies, and we can calculate it from a sample mean. So if we take a sample from our population and find its mean, then we can use that to find the mean, or an interval in which we're pretty sure that the population mean lies. And this is quite powerful because often for a population we're not going to know the population mean, and so we can just take a simple sample and then calculate or get an idea about where our population mean is. So if, for example, just to put that in a concrete kind of example, say we wanted to know the population mean of heights of Year 12 students at Gunga High School, then we could use this particular class as our sample, find the mean of the class, and then use it to give us an interval in which the population mean, so the mean of all the heights of all Year 12 students at Glenunga, would lie. Some of this is going to make a little bit more sense as we go through it. So confidence intervals, as I've already said, are a method used to say something about a population mean on the basis of a sample mean. So they're an interval or a range in which mu, which is the population mean, lies, and we have an associated level of confidence with them. So these can be calculated based on a sample mean or a proportion. So the proportion at the moment is not important. That's going to relate more when you get into binomial distributions. So in the language of statistical inference, we use the idea that what will happen in the long run gives us an idea to express a confidence in the results we've got. I'll come back to this point a little bit later when we talk about how to look at a confidence interval and how to interpret a confidence interval. But for the moment, it's probably not going to make a huge amount of sense, but do trust me, I will come back to this. So the language of statistical inference uses the principle of what will happen in the long run in order for us to express a confidence in the results of any one sample. In this course, only the 95% confidence interval is examinable. That'll also make a bit more sense as we go through. So we want to develop a 95% confidence interval for a population mean. So what that really means is if we want to get an interval and say, okay, we're 95% sure that our population mean lies in this interval. So if we work on our theory from the central limit theorem, we know that when we take samples a repeated number of times and find their mean, and build up the distribution of the means, then we get a normally distributed distribution, and it has a mean which is the same as the population mean, and a standard deviation equal to sigma over root n. Okay, now if we want to standardize this particular distribution, then the value of one particular sample of our means is the standard value for that is just going to be equal to x bar take mu, and that's all going to be divided by our standard deviation, which is sigma on root n. Okay, so that's just our Z statistic for one particular sample mean, and just to remind you, our Z distribution is normally distributed with a mean of 0 and a standard deviation of 1. So that's just some preliminary stuff. If you don't remember that, I encourage you to go back to the particular section which dealt with that. So to establish the 95% confidence interval, we want to find a particular value k for which the proportion of our sample distribution is between negative k and k, or between those two values. So what we're going to do is we're first going to find out what k has to be for our Z distribution to give us 95% of our Z distribution, and then we're going to map that back to the other distribution we were looking at. So if we consider the proportion of our Z distribution, that's less than or equal to k. So if we want the area in here to be 95%, then we're going to have to, then the area outside there and outside there is going to have to sum to 5%. And because it's a symmetrical distribution, then each one of these areas is going to have to be 0.25, or so 0.25%, or really as a decimal we could express that as 0.0025. Okay, so if we use the inverse normal function, so inverse, that means that negative k is going to equal the inverse normal. Now we're looking at the area to the left, because we're looking at this value here, so it's the area to the left. That area is going to be 0.0025, express it as a decimal, with a standard deviation of 1 and a mean of 0. Now in the textbook, I'll just make a quick point as we're going through. The inverse normal, Hazy puts it in a different order. That's because he's doing that for the TI calculator. In the Casio, the standard deviation comes first. So that tells us that negative k is going to be equal to negative 1.96, and then that tells us that k is equal to 1.96. Okay, so within our Z distribution, if Z is between negative 1.96 and 1.96, then the area in between those two values is 95%. Okay, so now we want to map that back to the sampling distribution that we were talking about. So if we start with our interval, negative 1.96 less than or equal to Z, that's a sample that we're working with. Okay, so that means that negative 1.96 is less than or equal to, and I'm going to cheat here, so I'm just simply going to copy that there and remove the Z equals. Okay, so if we just substitute this value in here for Z, it's exactly the same thing, because that's what we established earlier. So that's going to be less than or equal to 1.96. And then if we take this interval and multiply both sides of our equation by sigma on root n, then we have a interval for x bar take mu. Now the reason we can multiply both sides or all of these sections by sigma on root n is because inequalities work exactly like equations. So there's no difference. We can multiply all the sections here by sigma on root n, so we get a sigma on root n there. The sigma on root n in the denominator here disappears, and we get another sigma on root n there. Okay, so I'll just make a note of that what we're doing is multiplying by sigma divided by the square root of n, and then what we can do is we can go through and divide each of these sections by -1. But remember, if you go back to your inequalities, you remember that when we do that, the inequality sign has to change, has to be reversed. So if we do that, so if we divide this one by -1, that negative gets removed and this inequality sign changes. Here, if we divide it by -1, we're going to get mu take x bar, and the inequality sign is going to change. And then if we divide this by -1, there's going to be it's going to become -1.96 times by sigma on root n. Okay, and then really quite simply what we do is we look at this inequality here, and this is saying that mu take x bar is greater than or equal to -1.96 sigma on root n, and it's less than or equal to 1.96 sigma on root n. So really what that means is if we put a negative sign here and swap that sign to be a less than or equal to sign, and then take away the negative there and change the sign again, well, that's saying that mu take x bar is greater than or equal to -1.96 sigma on root n, and it's less than or equal to 1.96 sigma on root n. So it's saying exactly the same thing as we had up here, but we've just established a conventional order. And then really we want to get our interval for our population mean, mu, and so all we simply do is add x bar to all sides of the equation. So if we add x bar to this side, we get x bar take all that. If we add it to this section, we just get mu left behind, and if we add it to this section, we get x bar plus all of what we have there. And so this is the 95% confidence interval for the true population mean. So the reason it's a 95% confidence interval is because if we have a look back up here, 5% of the time the x bar, so the mean of our samples, is going to lie outside this interval in here, and when it does, this interval is not going to give us, is not going to include mu. So really only 95% of the time will this confidence interval include our population mean. So if we wanted to ensure that we always capture our population mean, we could increase it to say a 99% size, but then we'd have to increase our interval, and so we'd have less of a hold on exactly what our mean is. So the smaller the interval tells us more about what our mean is. The larger the interval, the more sure that it includes the population mean, but the less sure or the less detail about the population mean